All right, thank you very much, and glad to be here and really excited about the opening of Prime and looking forward to seeing what we see with this summer. So I'm going to be talking about Milky Way black holes and how to find them. We've had some excellent introductory talks. I'm going to be zooming in a little more on the astrometry side of things, but actually I wanted to give you kind of a comparison of what black hole microlensing looks like compared to exoplanet microlensing in general. So for black holes, as you heard from Shemek earlier, we're very motivated by trying to understand the population of black holes as a whole. We have a lot of uncertain questions, a lot of uncertainties, despite the large number of black holes that have now been detected by LIGO. We still don't know really simple things like what stars turn into black holes versus neutron stars, for instance. Or do they get kicks? Or do primordial black holes even exist? So this is what's driving all of us. And there are many ways to study black holes, not just microlensing, as you also saw from the plot. Here I've now zoomed into just those black holes with mass measurements in the Milky Way, where we can understand the host galaxy properties. Remember, the LIGO black holes, we have no idea what kind of galaxies they're happening in, don't know what their metallicities are. They're really a tip of a long population of close binaries that we're not going to be able to understand until we can understand their host galaxies. So in the Milky Way, where we have lots of information, we can study black holes through EM emission predominantly, X-ray binaries being the dominant mode for measuring masses of black holes, but also now detached black holes with a star companion and watching the star wobble, and now microlensing, which is sensitive both to isolated black holes and binary black holes. So the number is still very small in the Milky Way, and we're all racing to increase this number to keep up with the LIGO population. So in microlensing, we've been doing a lot of work over the years to figure out how best to look for black holes with microlensing, and that's relied on population synthesis work. This is showing the popsicle simulations that you saw so much in Zophia's talk earlier. We're really looking at two types of parameter space. The photometric, which is on your left, that's the microlensing parallax versus the Einstein crossing time. You can see the black holes do separate nicely, but there's no error bars on those points. This is simulation. And if you put the error bars on it, the parallax errors are ginormous. So while it separates nicely, our measurements aren't quite as good, quite good enough today to be able to clearly separate a single event into the black hole space. That's where the astrometry comes in, and that's the parameter space shown on the right. That's microlensing parallax versus the maximum astrometric offset you get during a microlensing event. And so here, there's a hard line, basically, or nearly so, where the black holes fall. And so if we can put these two together, as you saw, we can measure the mass. And then we have to also couple that with the blend fraction to just rule out massive young stars, for instance. Okay, so here's all the ingredients that go into finding black holes. We have to have first photometric surveys to find the microlensing events. Somebody needs to tell us there's a microlensing event and it's not a supernova or a flare star. Then we need to trigger astrometric follow-up, at least today. Then we have to do all of our microlensing modeling and population simulations, and I'll walk through each of these and tell you a little more about them. So first, the photometric surveys. An ideal photometric survey for black hole searches would have a cadence of 3 days or less. We don't need high cadence, but we do need long duration. These events last a long time. Even photometrically, they can last 5 years or more. We would really like to have maximum sensitivity to that microlensing parallax. That means we want to observe into the springs and falls of the year at opposition as much as possible. And then we think black holes concentrate more towards the plane of the galaxy, especially if they don't get big kicks, which we don't actually know what black hole kicks are. So looking in the galactic plane or the galactic center is a really nice place to look for black holes. Different photometric surveys play different roles. We've heard all about the new surveys that are coming online this year for Rubin, a few years from now for Roman. Each have their place. For Roman, it's best spatial resolution, best cadence, very sensitive, covers the galactic center. But there's a huge con from the black hole side of things. Those seasonal gaps, so remember, Roman only has 70-day windows. As you see in the bottom plot here, that's really painful. We can't take much out of the microlensing event if we don't also measure within the Roman gaps. So that's critical. Rubin, for instance, is best sensitivity and best area coverage, but the spatial resolution means blending is always a challenge. And the cadence is a little slow on the Rubin side, the greater than 3-day cadence, especially for same filter. So it too needs some help. And that's where all of the other 4 meter, 2 meter class photometric surveys come in. There's a lot of room to provide extra cadence or extra area moving outside the bulge alone, where Roman will look. The cons are spatial resolution and sensitivity, but the bright events are the ones that are easiest to characterize anyways in the end. So now on to, if we identify our microlensing events, we have to have some method of telling the world where to trigger and which events to trigger astrometric follow-up for. We need these detections and alerts to tell us on cadences of roughly a week, not instantaneously like a supernova team. And importantly, ideally from this system, we would need some kind of posteriors on TE and PIE. As you saw Zophia's talk, the classification really depends on that. And we can tell whether something's a black hole to high probability if we have full posteriors, which is not something we get out of today's alert systems. But we're working on it. In our group, we've been developing, riding on the heels of, I'd say, time domain astronomers who've been doing this for a decade now with ZTF. We've built on top of Sky Portal, a new portal that offers up a list of all the microlensing events we ingest, and we automatically fit with parallax models all the light curves that we get out of the alert warning systems and provide fancy interfaces. You know, this is just a trial for us to see if this works. Most importantly, it builds on existing time domain infrastructure. We move to automated classifications, and it has, within this, it has interactive alerts and collaborative platforms. I think that's really the way of the future for all the alert systems. And so I hope we're all looking forward to how to improve our current systems. All right, now onto the astrometric follow-up. Here, we're talking about cadences of, less than a month is doable, is sort of the minimum cadence. We need very good precision, 0.1 milliarc seconds or better. And we need a decent sized field of view, ideally 30 arc seconds, to get enough reference stars to establish the astrometric reference alignment. So you saw some examples of astrometry plots before, but here's the one detection that we have with real data and shown in blue from HST. You can see it's pretty sparsely sampled. It's a clear detection, but it's not great. It's going to be a revolution when Roman comes online because we don't have to trigger astrometry, we get it for free. That's what's shown in orange. And there, the precision of the measurements is much, much better just by sheer number. And the coverage of the light curve or the trajectory is much better. In fact, you can see we can actually measure the parallax signal during magnification and after magnification, which is extremely helpful for finding black holes. That gap filling is also critical on the astrometric domain as well. So we can't just rely on Roman astrometry alone. If there's big gaps in Roman, are going to be a problem for black holes, especially if they occur at particularly sensitive times. So here's an example of, on the left, the old school Roman survey that was planned, and on the right, what we're hoping to get through the ROTAC, which is gap filling measurements. Less frequently, not 15 minutes, more like once every 3 to 5 days. But that's good enough to help fill in the gap and get that astrometric signal really nailed down in the big gap between the seasons. That's not the only way. We should also think ambitiously and think for the future. And Shemek's talk about the interferometry is, that's phenomenal applications. We don't have to do it with an interferometry alone. We could do this on existing 8 to 10 meter telescopes if we can push our adaptive optics capabilities up to the visible. So this is showing a simulated microlensing event for a 20 solar mass black hole that's at 1 kiloparsec from us. Not a crazy possibility. If we could build a visible light AO system on Keck, for instance, we can achieve below 15 milliarc second spatial resolution. And you can see on the right the mock image with a realistic PSF for AO. Suddenly, during the event, you can see the secondary image. And so again, just like Shemek highlighted, we can take one picture, one snapshot, instead of having to monitor for 10 years a microlensing event and measure its mass. Microlens modeling, we have to put all of this data together into a coherent way. I'm going to stress we need modeling capabilities that can do joint modeling of astrometry and photometry. Bayesian inference is ideal. We have to be robust to degeneracies, and of course, binaries are all over the place, so we have to be able to model those. There are a lot of codes that have some astrometry support, but I think Bagel is the one where we can simultaneously fit astrometry and photometry right now. So if you're interested, you can take a look. We're about to have a series of papers submitted on Bagel, but the code itself has been public for a while. Yeah, good. So I just wanted to leave a little time using the modeling code to build you some intuition on astrometry and something we don't think about very much, which is blending in the astrometry. So interpreting our astrometric signals is going to get tricky, and we don't do this a lot today. So we need to think carefully about what we're going to see, especially when Gaia data is released, for instance, or when Roman turns on. So what I'm showing you here is the photometric light curves at the top. These are all point source, point lens events, but different blendings. So that's the no blended case is the orange, and then increasing blending into green and blue. The two bottom plots are the RA change with time and the DEC change with time. Again, blended and unblended. And the lens is in black and the source is in red, which is under the orange. You can barely see it. The bottom is where most of the astrometric microlensing signal is, so focus on that one for now. And I'll point out a couple of things. Number one is, even outside of the microlensing event, the parallax you measure is not the parallax of the source star or the parallax of the lens star. It depends on both of them. So that's one thing we have to be careful. Those long-term Gaia measurements, you can't interpret the Gaia parallax as always the source star. The other thing is you can see that the amplitude of the parallax signal changes with time. It actually can both increase or decrease during the microlensing event. And then finally, the last thing is you can actually have blending increase the astrometric microlensing signal. Look at the blue curve in particular. So the event is going along and then it shows a very large excursion, even though this is a one solar mass object. That excursion is because it was a low U0 event, a high magnification event. And so the source star got very bright temporarily, and it really shifted the astrometry in favor of the source star. That has very little to do really with microlensing and far more to do, well, very little to do with astrometric microlensing and far more to do with photometric microlensing. So the point is, for those of you who are interested in host stars of planets and their masses, you should be caring about astrometry too, because these astrometric signals may be something that you can detect. Here's what it actually looks like on sky with those different blendings. Orange is the unblended, green is increasing blending, blue is about 40% blended. So again, very different trajectories, very different shapes, and all of these signals will be very easily detected with Gaia. Sorry, not with Gaia, yes, but also with Roman. More importantly, I think for the cadence and sampling. So my message here is just, it's not just black holes for astrometry. We have a neat little calculator if you're interested. This is already available online. You can go play with the bagel models. And we support point source, point lens, binaries, sources, lenses, binary source and lens, all these kinds of things. I'll just point out that bagel is most useful when working with astrometry. When you want nested sampling inference or sort of really robust statistical methods and you've got compute power to spare. When you need to model red noise, we have that supported in our models, which is very nice. But most importantly, when you're not focusing on too extreme mass ratios, i.e. not planets. So we're happy to put more into Bagel. Bagel is completely open source, but at the moment, we just haven't spent our time and energy on making it really robust in the super high mass ratio regime. I will say, I don't know that it breaks for planets, so somebody should try it and see when it breaks. Okay, lastly, I won't spend much time on this. This is population simulations. You've seen a lot of this in the talks already. I pointed most of this out. But I'll just say that Popsicle includes stars, compact objects, kicks, binaries, triples, primordial black holes, brown dwarfs are in progress. Planets will follow right after that. Thanks. So it's pretty comprehensive. The biggest difference between Popsicle and almost all of the other population synthesis is that we make all the things. We don't just simulate microlensing events. And so I think it was Amon's talk who was talking about the standard model for exoplanets. This is the standard model for the Milky Way galaxy. It's the whole thing. Everything's in there. We could make use the same simulations to show sensitivities for binaries, transits, and microlensing events all in one. So that's really convenient, but does require a little more computational time. Things that are to be improved. We don't currently have binary evolution, dynamical evolution of the binary or mass exchange. Which if we wanted to predict LIGO populations, for instance, we need to add in. That's something we'd like to add in this year. Like I said, planets. And our black holes and neutron stars right now follow the stellar distribution. If they get big kicks, they should be puffier than the stellar distribution. And that's also a piece that's missing from the current simulation. And last, I'll just advertise, as you heard from Julie on the first day, Roman, we're all very excited about it from a microlensing perspective, not just for planets, but for black holes too. And we have this Roman science collaboration that's extremely broad, and I invite all of you to join. This just outlines some of the benefits that we think you can experience if you join the collaboration. And that QR code will take you to the Google form where you can fill it out and join if you'd like. And this will be ramping up quite slowly for the next couple of months, but of course, as we get closer to Roman, this gets more exciting. And that's it. Thanks to all my collaborators, and thanks again for having us, hosting us here.
Hi, I have a question coming from the another team that's dealing with parallax. How well are you able to constrain parallax with your models, especially before the peak?
On the, you're talking on the photometric only side?
Yes.
Yes.
Actually, astrometric side would be interesting too, if it improves.
Yeah, so on the photometry only, it's like a week for long duration events, TE is greater than 100 days. About a week before the peak, the parallax error bar really starts to shrink down. So that's about the time when we start to get confident. Yeah.
So nice talk. Let me ask you about the visible AO. How much resolution can you improve, and how much more expensive is it?
Yeah.
AO.
Yeah, so today's AO systems predominantly work in the infrared and deliver about 50 milliarc-second spatial resolution on the 8 to 10 meters. If we can move up to visible light, we can achieve, we think, realistically with today's hardware, 15 milliarc-seconds or better. The cost, we have to have something like 8 laser guide stars, 3 deformable mirrors, a bunch of wavefront sensors. It's not cheap. You can look at VLT Mavis for a kind of rough cost estimate because it's something close to that. That's also a visible light AO system. And we're talking about somewhere around 50 million, I would guess. So it's definitely not cheap, but it's cheaper than a space telescope. And habitable worlds, way cheaper than that.
Just a quick follow-up on this question. What is the astrometric patch for the video? How big the correction?
Yeah, so what we're aiming for, this is at the Keck Observatory where we're doing the current studies. We're aiming to build a multi-conjugate AO system with 3 deformable mirrors. So that would broaden, we wouldn't be limited to the isoplanatic patch. We would be able to have a corrected field of view of something about like 30 arcseconds, somewhere between 30 arcseconds and 60 arcseconds. That's also really helpful for the astrometry. It stabilizes the PSF. That's been one of the biggest weaknesses for AO is the field variable PSF in the past.